Okay. Um, so today we will be starting like the final topic of this course. So you have a couple of lectures on computational intractability or tractability, whichever way you want to look at it. Um, right. So what is this all about? So note that so far, whatever you have done in this course and possibly some other courses like data structures and even some other courses, we have mostly talked about problems for which we could design efficient algorithms, right? And what is our notion of efficiency? Well, formally we say that some algorithm is efficient if it's polynomial time. So there's a notion of polynomial time solvability of problems. Okay. So it's a characterization of computational problems. And remember, we are here only concerned about computational problems. So there are certain problems which cannot be solved using the notion of computation that we have, but we are not concerned about those problems. Yeah. So so what is polynomial time solvability? Well, if there exists an algorithm uh, that runs in time, something like, let's say, order n to the power of k, where k is a constant. Yeah. And n, remember, is the size of the problem. Size of the problem. And how do we define the size of a problem? Well, it's the number of bits. So hash bits required to describe the problem. Okay. So yeah, so we have talked about this issue of that it's really the number of bits that I require to describe a problem is what should be a reasonable way of representing the size of a problem. So, for example, if you are trying to solve the sorting problem, then you have to describe n different numbers, and let's say each number, the maximum value of any number is w. Then you need something like log w bits to represent each number, and you have n such numbers, so you need n times log w bits in all. On the other hand, if you want to solve the problem of, let's say I give you some number capital N and you want to find out whether this number is prime or not, then the size of the problem is not n. Okay, the size of the problem is just log of n, because log n bits are enough to represent this problem. So we tend to, whenever we see this n, we tend to think about it as, so depending on the problem. So when it's a graph, we say that, okay, it's the number of vertices and number of edges and so on and so forth. But in your mind, you should always have this correct notion, which is that it's the number of bits that you require to represent this problem or to describe this problem. Okay. And now if you can design an algorithm which runs in time something like n to the power of k, where k is a constant independent of n, then we say that this is polynomial time. Okay. And in fact, k can be quite large. Okay. Quite large and impractical. Yeah. So there are problems for which, in fact, we know algorithms which say run in time n to the power of 900, for example. Yeah. And in fact, there exist such problems where the best known theoretical guarantee that we can give about the running time is something like n to the power of 900, which clearly is not practical. But again, as we will realize that computational tractability is more of an academic pursuit. Of course, it's very important to coders and programmers who are trying to solve such problems, because it helps us know the limitations of the algorithms that we are designing. But honestly, it's more of a scientific pursuit. Yeah, so it's an understanding about the nature of problems, or the limits that we hit when we try to solve those problems using computers. Okay. So throughout this course, we have seen a lot of problems that are polynomial time solvable. So let me just list down some examples. So sorting, searching, uh, then what else? We talked about shortest paths. Yeah. We did not talk about minimum spanning trees, but I'm sure you have done this in your other courses. Also, flows, right? So all these are polynomial time solvable problems. Uh, but sadly, uh, this is not the case in most of this is not the case most of the time. Yeah. So sadly, there are many important problems, and when I say many, it's really, really many important problems uh, are or seem very hard to solve efficiently. Okay. So when I say that all these problems seems like they're very hard to solve efficiently, what I mean is that after years and years of research, we have not been able to come up with a provable algorithm which solves this problem correctly at every instance, and they all run in time polynomial in the size of the input. Okay. So it's not clear whether such algorithms exist or not, but we have not been able to find them. Okay, and we will see several examples of such problems. Yeah, where we have hit this bottleneck, or it seems to be very hard to solve. Okay, so now, as I said, this is more of a scientific discipline about what to do with those problems. So, okay, we don't know, we cannot seem to find efficient algorithms or provably efficient algorithms for this problem. So really there are two ways to, like, there are two directions which people take at this point. One is to just go along with some heuristics. Okay, so you study the problem, you have some domain knowledge of that problem, and you design some practical heuristics which you feel will work reasonably well in most of the cases, and you just go home happy with those heuristics. Okay, so that is surely one way. In fact, that's the most practical way to handle these problems. Okay, if you cannot find an algorithm which you can prove to be good, then better find something which is actually good in practice. Why not? Yeah, that's a reasonable pursuit. But what we will do in this topic, under this topic, is the other direction, which is delving deeper into these problems. Okay, so it's more about understanding the nature of these problems. More importantly, we ask ourselves the following questions: that are these problems somehow related? Are these hard problems somehow related to each other? Okay, so that is the sort of the moot question in this topic. So, and in other words, it concerns classifying problems according to hardness, according to computational hardness. Okay, good. So so there are several ways. So there's an entire area called complexity theory which deals with questions like this. The one which we will touch upon mostly for these 2 lectures is the notion of NP completeness. uh, right? Okay, and let me tell you straight away that this is a topic on which any computer science enthusiast should spend at least half a semester just on NP completeness. There are several aspects to it. We would not be delving so deep into this topic. We would just sort of touch upon it. We will know some definitions, although at a at not a very formal level, but we will at least try to understand, okay, what this means for all practical purposes. But yeah, I start this lectures with this caveat that what I am doing is by no reason a thorough treatment of this topic. It's just sort of showing you some initial notions of this thing. Okay. um, Good. So now let me start with an example of a problem for which falls into this class of problems that we do not seem to be able to solve efficiently. Okay, so example of a seemingly hard problem. Okay, so I'm sure all of you have heard about this. Probably the most, one of the super hit problems of computer science, which is the traveling salesperson problem. Okay, so let me tell you the problem straight away in a graph theoretic term. So I can always build up the fancy story of some salesman trying to visit a number of cities, and he or she is trying to sell something. So you have to find for them a tour where they would visit every city exactly once and come back to the starting city, and you should minimize the total amount of travel that they have to make, and so on and so forth. But let's cut out all that story and let's just straight away define this problem in a computational sense. Yeah, so we are simply given a graph. Yeah, so we are given an undirected graph, and every every edge has a length associated with it. So the setting is very similar to the shortest path problem or the minimum spanning tree problem. Yeah, so let's say the lengths are something like this: 1, 2, 4, 5, 6. Okay, and the goal is to find a minimum cost cycle that visits every vertex exactly once. Exactly once. Okay, there's a question. Is the graph complete? Not necessarily, because there might be cases where you might not be able to reach from, let's say, some point to some other point directly. So the only way you can reach is via through some other path, right? So it's not necessarily a complete graph. But it's true that uh, even for a complete graph, which is actually a special case of all graphs, we do not have an efficient algorithm to solve DSP. We can repeat edges, but if you repeat edges, then you are repeating vertices as well. So that's not allowed. Ashmi, does that answer your question? Yeah. Okay. So is the question clear to everyone? Okay. So that's the traveling salesperson problem. And so if you think about it, okay, so first of all, let's see what is a good tour in this case. So if I have done the thing correctly, then this is probably the best that you can do. Okay, I might be wrong, but it's up to you. So this is clearly a correct solution in the sense that it's indeed a cycle that visits every vertex exactly once. So if you want to, make the thing slightly more concrete, then you can think about a starting vertex as well. So you start at some vertex, you visit every vertex exactly once, and then you come back. Yeah, and probably this green tour is the cheapest cost tour. Okay. Now, if you think about it, this problem has uncanny similarity with the minimum spanning tree problem, right? So the minimum spanning tree problem asks for a tree which connects every vertex in the graph. So it seems like it's just a one-step generalization to that problem. Instead of a tree, all you are asking for is a cycle that covers all the vertices. But just this one tweak makes this problem notoriously hard to solve. Okay. So we don't know whether there exists a polynomial time algorithm to solve this problem. Okay. So one of the pioneers of the field of algorithms, a person by the name of Jack Edmonds. So he had conjectured long back, yeah. So I don't remember the exact date, but he had conjectured that TSP does not admit efficient algorithms. Okay, so this is a conjecture. We don't know. So this was probably done like 30, 40 years ago, but it's still open. So this thing is not resolved yet. We don't know whether TSP admits an efficient algorithm or not. Okay. So this is very important to keep in mind. Hard problems doesn't mean that there are no algorithms or no efficient algorithms to solve. It just means that we don't know efficient algorithms to solve these problems. Yeah. There are certain problems, of course, for which we know that there cannot exist an algorithm, and I will mention one such algorithm in our discussion, for which it's not possible even to design an algorithm that will terminate in finite amount of time. So no matter for how long you run your algorithm, it will not give you the correct answer. Okay. So there are such problems, but TSP is not one of them. Okay. In fact, let me ask you, can you think of a finite algorithm for TSP? So let's say I don't care about efficiency. So what is an algorithm that will at least terminate in finite amount of time and give you the correct result? Exactly. So all possible cycles. Yeah. So just try all possible solutions. So you take your, so essentially, if you think about it, you just need to check for all possible permutations of the vertices, right? So you check for all possible orderings and you see which one of them gives you a valid cycle and which one among them is the least cost one. So that's a perfectly valid algorithm. Well, it takes exponential time. That's fine. I mean, if your graph is not too large, I mean, and with today's computational power, this is a perfectly valid algorithm to try out. Why not? Okay. But yeah, that's exponential time. It's a brute force algorithm. It's not efficient in the sense that we define efficiency. Okay, good. So now, what the complexity theorists or the theoretical computer scientists started to do was the following: that suppose I want to resolve this question. Suppose I want to resolve the question that TSP is hard or not. Okay. So what I mean is, so suppose I want to prove, so want to prove formally. Yeah, so efficient algorithms mean polynomial time. That's correct. Yeah, polynomial in the size of the input. Suppose I want to prove that ESP is hard. Okay. So what could be possible ways of proving such a thing, that this is really really hard? So, or at least can we amass enough evidence of this fact that this is a really hard problem to solve? Yeah. So one direction which people started taking was the following, that is the following statement. or to sort of check whether the following statement is true or not, is the following: that if you can solve TSP efficiently, then you can solve many hard problems, many other hard problems. Okay. So, in order to convince ourselves that TSP is really hard, one way to do it is to sort of prove the following thing: that if you are able to find an efficient algorithm for TSP, then you will find an efficient algorithm for many other problems with which people are stuck for a long time. So they are of the kind of the same status as TSP is. So probably for all of them, you can find a brute force algorithm, just like you have found for TSP, but we are not being able to find an efficient algorithm. The question is, can we prove a statement like the following: that any solution to TSP can be translated in polynomial time to a solution for those problems? Now, the point is, proving this statement, of course, does not prove that TSP is hard, or TSP is, there does not exist any efficient algorithm. Clearly, that does not prove this fact, but at least it's amassing evidence towards the fact that this is a really hard problem to solve. In fact, all those problems are really hard to solve. Okay, so this is this entire. I mean, this lies at the heart of this notion of classifying problems according to the level of hardness. Okay, so I'm being deliberately vague at this point. We will make this notion at least slightly more concrete over the course of the lectures, um, and then we will see. Okay, there's a question: is this been proved? What has been proved? That if you can solve TSP efficiently, then you can solve many other hard problems. Yes, so that's all we will see. That there are a whole lot of problems which have this characteristic that if you are able to solve even one of them, then you will end up solving all of them in polynomial time. Yeah, that's the whole content of these two lectures. Okay. Now, so let's start by making this notion a bit more formal. Okay, so we will use some technical terms. We won't be saying this thing again and again that, okay, if you can solve problem A, then you can also solve problem B. So we will not use this very mouthful statement every time. What we will use instead is the notion of reductions. Okay, and when I speak of reductions in this course, I always mean polynomial time reductions. So polynomial time reductions. Okay. So, okay. So what do I mean by reduction? Well, I essentially mean exactly what I have written above, but let me, so this is again a bit informal. So informal definition. So we say that, so let's say I have a problem pi 1. Okay. So I say that it reduces to the problem pi 2. Okay, so so please remember this direction. Okay, so this is more like less than or equal to, which somehow means that problem 2, a problem pi 2 is at least as hard as problem pi 1, in the sense that, if you have an algorithm to solve pi 2, then you will also have an algorithm to solve pi 1. So this is what this less than equal to kind of symbol means, right? So this means that problem pi 1 reduces to problem pi 2 in polynomial time. So the P stands for polynomial time. Okay, so that's the notation that we are always going to use. So this means given, yeah, so we will see all that. So this means given a polynomial time for pi 2, we can design a polytime algorithm for pi 1. Okay. So Laksha, to answer your question, this is precisely what it means. Okay. So this is the definition, that if you have a polynomial time algorithm to solve pi 2, and you can design a polynomial time algorithm to solve pi 1 using that algorithm, then you say that the problem pi 1 reduces to pi 2. Now, how you do that reduction depends on the problems that you are talking about. So there is no fixed recipe. Then there is no fixed recipe to to do the reduction. But we will see that in most cases it falls in a certain recipe. Okay. So okay, there is another question. If later it is proved that pi 1 doesn't have a, okay, that's a great question. So Lakshay is asking the following question. In fact, that's precisely what I was going to say next. So what he asks is the following, that if somehow, now let's say that you are able to prove this fact for problem pi 1 and problem pi 2. And now later you somehow, someday you happen to prove by some other technique that pi 2 does not have a polynomial time solution. Then what does this imply? Does it imply anything? Okay, very good. So this is a common confusion that we all have when we start studying reduction. Okay, let's think about it. So some people are asking the following question, that if pi 1 reduces to pi 2, then if I rule out the existence of a polynomial time algorithm for pi 2, can I rule out the existence of a polynomial time algorithm for pi 1? Is this statement correct? Exactly. Good. So some people have also answered this question. So this is not guaranteed, right? Because there might be some other way of designing a polynomial time algorithm for pi 1. Okay. So designing a polynomial time algorithm for solving pi 1 does not necessarily have to go through designing a polynomial algorithm for pi 2. That's not clear. Okay. Good. So that's not implied here. But what is really implied? Can we imply something of the kind which you are saying from the statement? So which direction can we really imply? Very good. Okay, so let's actually list down what the two things that we can imply if we have such a reduction. So implication one. So let's say implication one is that okay, so yeah, the first implication, of course, is the definition, right? That if you have an algorithm for pi 2, then you can, given some problem pi 1, you can probably do something and use pi 2 in some way to solve pi 1. However, the other implication is, if we prove there does not exist a polynomial time algorithm for pi 1, okay, then pi 2 does not have a polytime solution. Okay, that's the implication of the above statement. And the easiest way to see this is to think of the opposite case, right? So suppose there does not exist a polynomial time algorithm for pi 1, but there exists a polynomial time algorithm to solve pi2. But because I know that pi1 can be reduced to pi2, then this contradicts our assumption that there does not exist an algorithm for pi1. Yeah. So please remember that when you reduce pi1 to pi2, then if you prove that pi1 does not admit a good solution, then you can conclude that pi2 will not also have an efficient solution. Okay. So this is the whole crux of doing all this reduction. Okay. So the idea is now, so today we will actually see some concrete example of how to do such reductions. So as Lakshya was asking that, what do you really mean by reduction? What do I mean by this fact that given a problem, I can reduce it to another problem and use its algorithm to solve the other one? Okay. So today we will see some examples of how these reductions work. And in the next lecture, we will actually make the notion of, we will introduce the notion of NP problems and NP complete problems on the basis of this definition of reductions. Yeah. So all those definitions crucially rely upon our understanding of reductions between problems. Yeah. At a high level, what we want to do is what we started off, that we are going to show, for example, that there are several hard problems, say, which can be reduced to solving TSPs. Yeah. So if you can solve TSP, you can solve all of them in some sense. Yeah. So let me, okay. So by the way, speaking of reduction, so the point is we have already seen, although implicitly we have not explicitly used the term reduction too often, but we have seen several examples of reduction in this course. So can someone tell me what are some examples of reduction? So, have we done this, like reducing one problem to another? So using our knowledge of one algorithm to, algorithm for one problem to solve a different problem. So have we seen this in this course? Yeah. So yeah, exactly. Yeah. So we have seen this several times, in fact. So we have seen that, for example, the problem to find the maximum matching in a graph can be reduced to the problem of finding maximum flow in a graph. And remember this reduction is polynomial time. Why is the reduction polynomial time? Because given an instance of the maximum flow problem, you only need to spend polynomial amount of extra work to convert it to a max flow instance. This is very important. So this is why, informally, this is what we what we mean by a polynomial time reduction. So the reduction itself should not take something like exponential time. Then all this breaks down. Yeah. But of course, when you convert a maximum matching problem to a max flow problem, it's clearly a polynomial time reduction. So that's one. So example is, let's say, max cardinality matching. Reduces to max flow. Yeah. But in this case, of course, we know polynomial time algorithm to solve both of the problems, right? So this implication one does not really kicks in for this case. Okay. So Raghav has given one more example where we reduced the subset sum problem to knapsack problem. That's also a valid example. Yeah. So given an instance of the subset sum problem, you can reduce it to solving a knapsack instance. And again, this reduction works in polynomial time. But note that this is an interesting example which came up because there none of the algorithms are polynomial time. Okay, why are those not polynomial time? So remember, what is the runtime of knapsack? So what he says is subset sum reduces to knapsack. Okay, so So remember, what was the runtime of knapsack? It was something like order n times w, where w is the size of the knapsack, size of sack. Okay. And please remember, this is not polynomial time. Yeah, this is pseudo polynomial time. And why is this pseudo polynomial time? Well, because I only need like log w many bits to represent w, but my runtime is depending polynomially on w. So this is clearly there is an exponential gap. So think about the scenario when n is really, really small and w is really, really large, then this is clearly exponential time. Okay. Okay, so there's one more question. Can you please explain the symbol? Yeah, this just means that subset sum reduces in polynomial time to knapsack. So this means that if I give you an algorithm to solve knapsack, then you can use that algorithm to solve subset sum. This is all this means. Yeah, there's nothing much more to it. I mean, I can give you the formal definition, but this is really what it means. Yeah, that if I give you a polynomial time algorithm for problem 2, then you can use it to solve problem pi 1 in polynomial time. Okay, and we will see today examples of how to do these reductions formally. Okay, so let's go on to then. Okay, so examples of reduction. So examples from one hard problem to the another. Okay, good. Uh, so remember again, when I'm talking about hard problems, I have not formalized the notion of what is a hard problem. So for now, hard for me, for us, just means that we don't know an efficient algorithm to solve these problems. That's it. Okay. So let me actually start by giving you examples or names of some problems, and we'll be talking about some of them in these lectures. Okay. So the granddaddy of all these problems is the satisfiability problem. Okay. There is an easier version or a seemingly easier version of this problem, which is known as the three sat problem, which is also hard. Okay. Then we talked about TSP already. Then we can think about the independent set problem, independent set, vertex cover, okay, Steiner trees, and so on and so forth. Yeah, hundreds and hundreds of problems I can list out. In fact, I can post a link on the web page, which has a great collection of problems of this class for which we know brute force algorithms, but we don't know efficient algorithms to solve them. Yeah. So if you're interested, uh, you can take a look at the list. And in fact, I'm sure what we will realize eventually is in many of your projects, you will actually bump into one of these problems today or tomorrow. Okay. And then you will realize that, oh, this is a hard problem. So maybe I should not try to find an efficient algorithm for this because it seems hard. But let's just, rather find some smart heuristic to solve this problem. Okay. So that is why it's important to at least know about these problems. Okay. Um, Great. So let's see an example of a reduction. Okay. So the first reduction that we are going to do is, okay, so before that, let me actually talk a bit about decision problems. Okay, let me start by defining the problems that I want to show a reduction on, and then I will introduce you to what we mean by decision problems. Okay, so independent set or max independent set reduces to vertex cover. Okay, great. So what is the max independent set problem? So suppose I'm given a graph. something like this maybe. Okay, so let me just draw the graph again here. Right. So what is the independent set problem? Well, it asks you to find a subset of the vertices such that there are no edges in between any pair of them. Yeah. So that's the independent set problem. So any such set is an independent set. Trivially, the null set is an independent set. But of course, our idea would be to find the maximum sized independent set in a graph. Okay. So if you think about it, the maximum size independent set in this graph is these three vertices. Okay. I cannot add any of the other two vertices in my independent set because that will not be feasible, right? It will have an edge to one of the things that I have already added. And indeed, it turns out that this is indeed the maximum independent set. It's not only maximal, but it's also maximum. Okay. So this is a hard problem. We don't know how to, so in a general graph, uh, we don't know any efficient algorithm to solve this problem. Okay. By the way, uh, it's easy to solve this problem if your graph is just a path. And if you now look back at one of the quizzes that you have done, you were solving exactly this problem. In fact, you were solving a general version of this problem. So if I give you a graph, which is just a path, a simple path of some vertices, and I ask you to find the maximum independent set, then you can use a dynamic programming algorithm to solve that problem. In fact, we can do more. If I give you a tree, even then you can find the maximum independent set in polynomial time. Okay, but for a general graph, this seems like a hard problem. We don't know how to do that. Okay. Okay. So that's the independent set problem. Now, what's the vertex cover problem? Well, the vertex cover problem is somehow it's a complementary. It says that give me a bunch of vertices. Yeah, give me a bunch of vertices such that they cover every edge in my graph. Okay. So what do I mean by cover? It means that you give me a bunch of vertices such that every edge has at least one endpoint incident on this set. Okay. So again, it's best explained by an example. So if I pick these two vertices, then that's a valid vertex cover of my graph. Why? Because if you look at any edge, then this edge is incident on either the red vertex on the left or the red vertex on the right. So that's a valid vertex cover of the graph. Yeah. So let me just write these two statements down. So independent set is find the maximum size subset of vertices such that there are no edges between any pair. In that subset. Okay, and this is find the minimum size subset such that subset of vertices such that every edge is incident to some vertex. That's it. Okay. Any questions about these two definitions first? Okay. Is it clear? Is the definition clear for both? Right. So again, a trivial vertex cover would be to take all the vertices in your graph. That's a feasible solution, but Of course, that's not a minimal solution, or that's not a minimum possible solution. Yeah, you can clearly see in this picture, if you just take these two red vertices, that's a vertex cover. Okay. So now we will see that we can reduce the problem of solving independent set or maximum independent set to essentially solving the minimum vertex cover problem. Okay. But before that, I need to introduce you to what we call decision problems. And the reason I'm doing this is because the notion of, so first of all, as we will see that decision problems are ubiquitous in the sense that if you are able to solve the decision version of these problems, then you will also end up solving the optimization versions of this problem. Yeah, we will see why. And secondly, the notion of NP hardness or NP completeness lends itself very nicely to decision problems. So we will be only concerned about decision problems from now on. Okay. So in the language of, okay, so what are decision problems? So they have only yes, no answers. Yes or no answers. Okay. So one example which you might have seen, I mean, of course you have seen, is a searching problem. Yeah. So I give you an array and I give you an element and I ask the question that uh, does this element occur in this array? That's a yes no question, right? You don't have to produce, you don't have to give me a number, you just have to answer a yes or no. So that's an example of a decision problem. Now it's not readily clear what is the decision version of, let's say, the maximum independent set problem. So let me give you that version. Okay, so independent set is given the graph G and an integer K, does G have an IS of size at least K? Okay, so I give you a graph and I also give you some positive integer K, and I ask the question that does there exist an independent set which is of size K? So I'm not even asking you to find me the independent set. I'm just asking the question that does there exist an independent set or not? Okay. Now, okay. So remember, I claimed that this is somehow as good as solving the optimization version of this problem. So who can tell me why is that the case? So if I'm able to find a polynomial time algorithm to solve the decision problem, why should that imply that I also have a polynomial time algorithm to solve the optimization version or the maximization version? Okay, so first of all, k is less than equal to n, then very good, great. So here is an answer to that question. That suppose you have an algorithm to answer this question in yes or no, then what you can do is you can run this algorithm as a black box for all possible values of k. And in this case, the values of k can be only between 0 and n, right? So the maximum size of an independent set can take values only which are between 0 and n. So you just try this black box algorithm for every value of k, and that gives you like a polynomial time algorithm. By the way, do we really need to check for every value of k? Can we be more efficient? Okay, so think about it. I mean, we don't need to check for every value of k, right? Okay, first of all, very good. So once we get a no, we can stop. But the other answer is that you can do a binary search, right? So so you do a binary search and then you will be done in, let's say, log n rounds. You don't have to run your algorithm for n number of times, but you just run it for log n number of times. Yeah, great. So that's the decision version. So similarly for vertex cover, the decision version would be given G equals V comma E and K, does G have a vertex cover of size which is at most K? Right? So that's the decision version of vertex cover. Again, if you can solve this in polynomial time, you can do a binary search and solve the real vertex cover problem. Okay, so we don't know whether we can find efficient algorithm for them. But what I will show you now or convince you about is that if you give me a polynomial time algorithm to solve VC, then I can design a polynomial time algorithm to solve IS. Yeah. So theorem is IS reduces in polynomial time to VC. Okay. So why is that the case? So in order to do this, here is what we need to prove. Okay. So proof is so suppose, so there are two directions that I need to prove. Okay. So suppose S is an independent set in G. Okay. So suppose this is given to us that S is an independent set. So I am not concerned about sizes or size of S at this point. So just let's say I'm given this fact that S is an independent set in my graph, right? So let's actually look at this picture. So this is my set S, say. Okay, good. So if S is an independent set in my graph, who can tell me, can I conclude anything about a vertex cover in my graph? So if I give you this information that S is an independent set, then what can I conclude about vertex cover? Great. So I have several answers, and all of them are saying the same thing. So what they're claiming is that the complement of this set has to be a vertex cover. Okay, so let's at least verify this in this picture. So here S is an independent set, and if I look at the complement of that set, then that is precisely the set that I have marked here, and it turns out to be a vertex cover in this case. Okay, but why should this always happen? So let's verify this. Exactly. Okay, so the proof is as follows. The easiest way to see this is by visualizing the two sets separately. So suppose this is your set S, and suppose this is your set V minus S. Okay, that's the complement of S. So you have a bunch of vertices here, and you have a bunch of other vertices here. Okay. So the assumption that I'm starting with is that S is an independent set, which means there are no edges. There are no edges in this set, right? So this set is empty as far as edges are concerned. So every edge in my graph will either be, completely inside, or it would be something like that. Yep. Okay. So now suppose that V complement is S complement is not a vertex cover. Okay. But this clearly contradicts our assumption that S is an independent set. Why? Because if V minus S is not a vertex cover, then that means there exists an edge such that both the endpoints are part of S. But this is a contradiction because I'm assuming that S is an independent set. So that cannot happen. Okay, which means that V minus S has to be a vertex cover. Okay, everyone understands this point. So let me just write it down. So suppose S is an independent set. This implies that V minus S is a vertex cover. And the reason is, suppose not, then this implies there exists an edge between two vertices in S. ठीक है? And this implies a contradiction. Okay. So this is only one side. So what we have shown here is that, okay, what does this imply for the decision version? Well, the decision, it implies the following for the decision version, that suppose now I give you a K and I ask you the following question, that does there exist an independent set of size K? And suppose the answer is yes. The answer is yes, there exists an independent independent set which is of size at least K. Then that will readily mean that there exists a vertex cover which is of size at most n minus k. Okay, so that solves the decision version of vertex cover with the parameter k to be n minus k. Yeah, that's one side of the reduction. Okay, but of course we are not done. We have to also prove the other side, that suppose it's a no instance for IS. Okay, so this implies yes instance for IS on G comma K implies a yes instance for vertex cover on G n minus K. Okay. Now, the point is that the converse is also true, because what we just proved above is the converse be true hai. So suppose now I give you, now let V minus S or S complement be a vertex cover. Okay. Then a very similar proof. So you should think about it. I will not go into detail anymore. So this implies that S is an independent set. Okay, it's exactly the same proof. So if V minus S is a vertex cover, then S has to be an independent set. And it's very clear, because agar ye nahi hai, then there has to be an edge between, I mean, if S is not an independent set, then there is an edge between two vertices in S, which means that V minus S cannot be a vertex cover. क्योंकि उस edge को कोई cover नहीं कर सकता V minus S में. Okay, so it's the same thing, just in the other direction. And this now implies, so this implies that a no instance for IS on G comma K implies a no instance for VC on G n minus K. Okay, that's the proof. So that's an example of a reduction. Okay, so here is a recipe for doing the reduction, which you will always have to follow. Whenever I ask you to do a reduction from a problem pi 1 to a problem pi 2, you have to convince me that given a yes instance of pi 1, you can generate a yes instance for some version of pi 2, and vice versa. Given a no instance for pi 1, your corresponding pi 2 instance should always give you a no answer. Okay, so the reduction has to, or this transformation has to be done in such a way that these two properties hold. Yeah, in fact, this is a very easy example of a reduction, because we did not really construct anything. We just made this observation that if S is an independent set, then V minus S is a vertex cover. That's it. We did not really have to do any, we did not have to really construct a different graph or anything. Yeah, but we will see more involved examples where we indeed have to do some additional constructions. So before that, are there any questions about this? So let's take a pause for a minute. Okay. By the way, if you think about it, the same proof can also be utilized to show the other direction. So in this case, vertex cover also reduces to independent set. So these are mutually reducible. So you can either say IS is reducible to VC, or you can say VC is reducible to IS. Yeah, the same proof will work in this case. That might not be the case all the time, but in this case, at least this seems to be the thing. Yeah. So that's one observation. So now the next reduction which we are going to see is 3 sat reduces to IS. Okay. So what is the SAT problem now? So satisfiability. So this stands for satisfiability. Okay. And this belongs to a general class of problem which are known as constraint satisfaction problems. Okay. So these are known as CSPs, and they are a very useful object of study, especially in the field of theoretical computer science. Yeah, they offer a lot of it. So it's a fact that they also encode a lot of real life problems, but more importantly, they have extremely nice properties which help us understand the limits of tractability. Yeah, so CSPs are very important. Satisfiability is a special case of CSPs. Okay, so what's the problem? So the setting is fairly simple. I am given a Boolean formula. Yeah, but the Boolean formula has a specific nature. So suppose, so given uh, n Boolean variables, x1, x2 till xn, right? So they can take values either 0 or 1, and a Boolean formula with clauses C1, C2 up to Ck. Okay. And what is a clause? Well, a clause, so any Ci, it looks something like this. So it's suppose, okay, let me give you an example actually. So let's say x1, x2, 3, something like this. Okay, so that's my clause C1, and okay, and the formula looks like this. So you have k clauses where each clause is what we call a disjunction of literals. Okay, so what is a literal? So literals are either xi or xi bar. Okay, so that's what I call literals. So either it's a variable or the negation of that variable. Yeah. So each clause will contain a disjunction of the literals. Disjunction matlab or gate. Okay. So it's an or of these literals, and the entire formula is a conjunction of k such literals. Okay. मेरे पास k clauses है, and each of them is a disjunction of these literals, right? And now what is the question? So the question is, does there exist an assignment of each xi such that the formula evaluates to 1? Okay, this is the question that we are asking. कि ये जो हमारा है conjunction of clauses, is there a satisfying assignment to this formula? Okay, so let's see, is there a satisfying, so let's make this a bit longer. Yeah, so is there a satisfying assignment to this formula? might be or might not. Okay, so think of what you need to do, right? So if you want this conjunction to evaluate to 1, what you need to make sure is that every clause evaluates to 1 individually. Even if one of them becomes 0, then your entire formula just becomes 0. So you have to find an assignment of the x size such that each of these clauses C1 to CK, they evaluate to 1. Okay. So I don't know, maybe setting x1 to 1 will serve the purpose. x1 to 1 and x3 to 1 and x2 to 1. Probably, yes. Yeah. Okay. So if I just, so one solution is you set x1 to 1 and x2 to 1 and x3 to 1. Yeah. This clearly satisfies this formula. Okay. But as you can imagine, this is not necessarily the case always. Yeah. In fact, I can make a small tweak where probably this will not work. So I think if I just make this x2 bar, then probably this is not satisfiable. Probably. I might be wrong. Yeah, I'm not sure, but maybe. Anyway, you get the thing, right? So any questions about the definition of the problem? So I'm simply asking for an assignment of exercise so that this formula evaluates to a 1. Okay? Good. So yeah, so this seems like a hard problem. We don't know any efficient algorithm. So if I give you all these variables and this formula, and I ask you to design an algorithm to find this assignment, satisfying assignment, or even to answer the question that does there exist a satisfying assignment, it seems to be a notoriously hard problem to solve. Okay. So even a restricted version of this problem seems very hard to solve. So which is the 3-SAT problem. So the 3-SAT problem says that the size of or the number of, so SAT problem with number of variables or number of literals, let's say number of literals in each CI I equals to 1 to m exactly 3. Okay, so each of the clauses that I showed you above will have exactly 3 literals, right? So this is not an example. So the example which I showed above, this is not an example of 3-SAT. Yeah, because some of them has 2 variables, some of it has 1 variable. So if all these clauses have exactly 3 literals, then we say that this is a 3-SAT instance, right? Now it turns out that this is as hard as real SAT or vanilla SAT. In fact, you can show that vanilla SAT reduces to 3-SAT. Yeah, I'm not going to show you this reduction. You can think about it in the privacy of your home. So yeah, so given an instance of 3-SAT, you can actually generate an instance of 3-SAT such that a yes here will imply a yes here and no here will imply a no there. Okay. What we'll show today, or at least start proving, is that so theorem is 3-SAT reduces to IS. Okay, good. So let me show you the construction first, and probably I won't have time to go through the entire proof, but let's see how much we can do. Okay, so given a 3-SAT instance, okay, so remember, again, what's the recipe? So I'm trying to show that 3-SAT reduces to IS. Yeah, so I'm given an instance of 3-SAT, and now I have to generate an instance of IS such that this yes to yes and no to no business works out. Okay. So I'm given a 3-SAT instance, which means that I am given these variables x1, x2 up to xm, and I'm given these clauses c1, c2, ck. Okay. So given this, I will now generate a graph. Yeah. So of course I have to generate a graph. Why? Because I'm trying to reduce it to independent set problem. An independent set problem is defined with respect to a graph. Okay. So here is the graph that I generate. So for each CI, generate a triangle. Okay. So what does that look like? Well, so I take each of the clauses, and remember this is a 3-sat instance, which means that each of my clauses have exactly 3 literals. Yeah. So for each of these literal, I encode each of these literal in the form of a vertex in my graph, and for each clause, I use one triangle. Okay. So essentially, yeah, the reason that I'm using this triangle is that in a triangle, the independent set is really one. So yeah, and you will see why this is useful. Okay, good. uh, Now I will assign some labels to these things, right? So let me take an example. So suppose my formula is like this: x1 union x2 bar union x3 conjunction with x1 bar union x2 union x4, or let's say x2 bar x3 bar x4 bar. Okay, so suppose that is my instance for 3-sat. So what I do is I have generated these triangles for each of the clauses, and now I will label those with the literals. So this I label with x1, this I label with x2 bar, this I label with x3, this I label with x1 bar, this with x2, this with x4, and now I label this with, let's say, x2 bar. Okay, let me label this with x4 bar. This I label with x2 bar, and this I label with x3 bar. Okay, so that is those are the semantics of my nodes. Okay, further I do something more. Okay, so this is not enough to complete the reduction. I add some more edges in my graph. Okay, and the reason I add some more edges is the following: that so let's think for a minute of what I want. So what I want is, given, let's say I give you an yes instance of the 3-sat problem. Okay, so that's an assignment of the x1 to xm variables. So what I want is that this should somehow translate to an independent set uh, in this graph that I have created. Okay, so if I want that, yeah, so we will see why the triangles are interesting for that. But if I want this thing that some satisfying assignment translates to an independent set in my graph, then of the same size, right? So of the size k. So what do you think should be the other edges? Any intuition of what other edges can I? Okay, good. So the intuition is the following: that remember, if you look at a satisfying assignment, then both x1 and x1 bar cannot, if even in fact if you look at any assignment, both x1 and x1 bar cannot be 1, right? So if x1 is 1, then x1 bar has to be 0. Now if I want that the vertex with label say x1 is selected in my independent set, then I have to make sure that the vertex that I have labeled with x1 bar is not selected in the independent set, because then only I can do this transformation between between a feasible sat instance to a feasible independent set instance. Yeah, everyone understands this thing. So the intended semantics of this reduction is the following: that if x1 evaluates to 1, then x1 bar has to evaluate to 0. And if something evaluates to 1, I would like to take that vertex as my independent set, as a member of my independent set. So clearly I cannot afford to take both of them, because that will not translate to a feasible solution to my sat instance. ठीक है, at least at an intuitive level this should start to make sense. Okay, now what do I do in order to prevent that from happening? Well, by definition an independent set says that there should not be an edge between two vertices that you have picked, so I simply add an edge between these two. So we say that there is a conflict between these two vertices. Yeah, because one of them is labeled with x1, the other is labeled with x1 bar. So I simply put an edge between these two vertices. Similarly, I put an edge between x2 and x2 bar. I don't know, use an edge between x4 and x4 bar. I use an edge between x2 and x2 bar again. And I put an edge between x3 and x3 bar. Okay. So yeah, I might have missed some edge, but I think the idea should be clear. Okay. So any questions about the construction? We will finish the proof next time. So there are, some argument that we have to make, but is the construction at least clear? So one question is, should we not the same vertex? Should we not use the same vertex for x2 bar? How do you mean? No, so for each of the clauses, I make one copy of x2 bar. Okay, I understand your concern. So that is fine. Okay, so suppose you pick suppose you have picked the x2 bar version of the leftmost one and the x2 bar version of the rightmost one. Okay, but this is consistent with your SAT formula. You will just say that x2 bar is set to 1, which means that x2 is set to 0. That won't be a problem. What would be a problem is if you end up picking both x2 and x2 bar, vertices which are marked with both x2 and x2 bar, right? So it's not necessary that you have to keep one vertex for every literal. You should in fact keep one copy of every literal for all the clauses in which it occurs. Yeah. Okay, so Arundhati, yeah, we have not proved really that this is a reduction to the IS problem, but here is the intended semantics. So, okay, so here is what we are doing. So we start with our 3-sat instance, right? Now, so suppose I'm given this conjunction of clauses, right? So each of the clauses I know has 3 literals. Now, for each clause, I generate a triangle. Okay, I generate a triangle graph. I have 3 vertices, and I label each of these vertices with the corresponding literal. Okay, so for example, the first one I have labeled with x1, x2 bar, and x3. Okay, now so suppose now that suppose there is a satisfying assignment. So okay, let's let's just at an intuitive level think of the proof. So suppose there is an assignment, satisfying assignment to this clause. Okay, suppose there is an assignment of x1 and x2 and x3 and x4 such that this is satisfiable. Okay, so can you now create an independent set in this graph which is of size k? Okay, so this is what I'm claiming. So let there be a satisfying assignment. Okay, so the independent set that I will form is the following. So remember, if there is a satisfying assignment, तो इसका मतलब क्या है? इसका मतलब है कि every clause has at least one literal that has been set to 1. Okay, that's the only way that you can satisfy this thing, because it's a conjunction. So हर एक literal में हर एक clause में there is one literal which has been set to 1. There can be more than one. हो सकता है all the 3 literals are 1. That's fine. Okay, so I just take one clause at a time. So let's say I look at C1. I know that some literal in C1 has been set to 1. Now I come to my graph. Okay, I know that there is a vertex which has been labeled with this literal. So I just include that vertex in my independent set. Okay, ठीक है? So I just pick that vertex. तो ऐसे ऐसे मैं सारे clause के लिए I just pick exactly one vertex for each of the clauses. Okay, so pick one vertex for each literal in each for each for each literal in a clause that is set to 1. Okay, so for example, let's say I don't know if there is a satisfy, so maybe next time we will see a more concrete example. So suppose your satisfying assignment has set x2 bar to 1, okay, which means it has set x2 to 0. Okay, so then you will end up picking this vertex in your set that you are creating. Okay, so similarly, let's say you go to the next one and you found that I don't know, x4 has been set to 1, so then you pick this vertex. Okay, similarly, you go to C3, you look at which one has been set to 1, and you pick the corresponding vertex. Now, what we need to convince ourselves is that this forms an independent set. Of course, this set has size k because I'm picking one vertex for each triangle. But what's the guarantee that this forms an independent set? That needs to be shown. But I claim that that has to be true. Why? Because first of all, I have only picked one vertex from each triangle. So they cannot conflict with the other two vertices of this triangle. So the only thing that you can conflict with is some vertex which is not in this triangle, which is in some other triangle. But वो conflict अगर होता है तो उसका मतलब क्या है कि you have picked x2 bar, for example, let's say in C1, but you have also picked x2 in C2, right? But that cannot happen because exactly one of them has been set to 1 in your satisfying assignment. Both of them cannot have been set to 1. Okay, so this proves one direction, that given a satisfying assignment, you can generate an independent set which is of size k. Yeah, we have to also show the other direction. So let's do this in more detail next time. Yeah, okay. Okay, so let's end here today and let's meet on Thursday.